Using the equipment grounding conductor, also known as EGC, or the ground wire as a current carrying conductor is a bad practice for several reasons. Firstly, it creates a safety hazard. When the EGC is used as a current carrying conductor, it can become overloaded and overheat, increasing the risk of electrical fires. This is because the EGC is designed to carry only small fault currents, not the normal operating current of the circuit. Secondly, it reduces protection from electrical shock. The EGC is designed to provide a low resistance path to ground for fault currents, which helps to protect people from electrical shock. If the EGC is used as a current carrying conductor, it may not be able to provide this protection effectively. Thirdly, it can cause damage to electrical equipment. When the EGC is used as a current carrying conductor, it can cause damage to electrical equipment. This is because the EGC is not designed to carry the normal operating current of the circuit, and it may not be able to withstand the heat generated by the current. Fourthly, it is a code violation. Using the EGC as a current carrying conductor is a violation of the National Electrical Code (NEC). The NEC requires that the EGC be used only for its intended purpose, which is to provide a low resistance path to ground for fault currents. Using the ground wire as a current carrying conductor would be particularly dangerous because the cooktop is mounted in an island. This means that the ground wire would be carrying the current for the cooktop and the downdraft exhaust fan, which would overload the wire and increase the risk of electrical fire. If ever faced with a situation where you are being asked to use the ground wire as a current carrying conductor, you should refuse. It is important to put safety first and to follow the NEC. The equipment grounding conductor, or EG, is a vital part of any electrical system. Its primary purpose is to provide a safe path for fault current to return to the source, thereby tripping a circuit breaker or fuse and energizing the circuit in the event of a ground fault. This protects people from electrical shock and prevents damage to equipment. The NEC outlines specific requirements for the installation and use of EGC to ensure their effectiveness. One of the most fundamental rules is that the EGC must be a continuous, low impedance path from the furthest point on a circuit back to the grounding electrode conductor at the service equipment. This means that the EGC must be properly sized, securely connected, and free of any breaks or high-resistance connections. The size of the EGC is determined by the size of the circuit conductors, as specified in NEC Table 250.122. It's important to note that the EGC must be made of copper or other approved corrosion-resistant material. Connections must be made using listed connectors and fittings, and they must be wrenched tight to ensure a reliable electrical connection. The EGC must be run with the circuit conductors in the same raceway or cable. This ensures that the impedance of the ground fault loop is minimized, allowing for a faster and more effective clearing of the fault. There are several types of EGC that can be used depending on the application. These include wire-type EGC, metal raceways, and the metal sheath of cables. Wire-type EGC are typically used in non-metallic raceways and cable assemblies. Metal raceways, such as conduit, can be used as EGC if they meet certain requirements outlined in the NEC. The metal sheath of cables, such as armored cable or metal-clad cable, can also be used as an EGC if it is properly bonded to the equipment grounding system. Grounding electrodes are used to connect the electrical system to the earth. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. The grounding electrode conductor connects the grounding electrode to the equipment grounding bus at the service equipment. The NEC specifies the requirements for grounding electrodes and grounding electrode conductors in Article 250. It's crucial to ensure that the grounding electrode system is properly installed and maintained to provide an effective path for fault current to ground. Bonding is the process of connecting non-current carrying metal parts of an electrical system together to create a low impedance path for fault current. Bonding is essential for preventing voltage differences between metal parts, which can create a shock hazard. The NEC requires bonding of all metal enclosures, raceways, and other metal parts that are likely to become energized. Bonding is typically accomplished using bonding jumpers, which are conductors that connect the metal parts together. The size of the bonding jumpers is determined by the size of the circuit conductors as specified in NEC Table 250.102. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock by detecting ground faults and interrupting the circuit. GFCIs are required in many locations such as bathrooms, kitchens, and outdoor areas where there is a high risk of electric shock. When a ground fault occurs, a small amount of current leaks to ground. The GFCI detects this leakage current and quickly interrupts the circuit, typically within a few milliseconds. This prevents a person from receiving a dangerous electric shock. The NEC requires that GFCIs be tested regularly to ensure that they are functioning properly. Arc fault circuit interrupters, or AFCIs, are devices that are designed to protect against fires caused by arcing faults. Arcing faults occur when electricity jumps between two conductors, creating a high-temperature arc that can ignite nearby materials. AFCIs are required in many locations, such as bedrooms, living rooms, and dining rooms, to protect against the risk of fire. When an arcing fault occurs, the AFCI detects the unique characteristics of the arc and interrupts the circuit. This prevents the arc from igniting a fire. The NEC requires that AFCIs be tested regularly to ensure that they are functioning properly. The electrical safety is paramount, and understanding the role of the equipment grounding conductor is essential for ensuring a safe electrical system. By following the requirements of the NEC and using qualified electrical contractors, you can minimize the risk of electrical shock and fire. Remember, when in doubt, consult with a licensed electrician or electrical engineer to ensure that your electrical system is safe and code compliant. Electrical codes and standards are constantly evolving to address new technologies and safety concerns. It's important to stay up to date on the latest requirements to ensure that your electrical system is safe and compliant. The NEC is updated every 3 years, and it's essential to review the latest edition to understand any changes that may affect your installation. Additionally, there are many other organizations that develop electrical standards such as UL, ANSI, and IEEE. These standards provide detailed requirements for the design, construction, and testing of electrical equipment and systems. It's important to be familiar with these standards and to use equipment that is listed and labeled by a recognized testing laboratory. Regular electrical inspections are crucial for identifying potential hazards and ensuring that your electrical system is safe and code compliant. Electrical inspections should be performed by qualified electrical inspectors who are familiar with the NEC and local electrical codes. During an electrical inspection, the inspector will examine the electrical system for any signs of damage, wear, or improper installation. They will also test the system to ensure that it is functioning properly. If any problems are identified, the inspector will provide a report outlining the necessary repairs or upgrades. Regular electrical inspections can help prevent electrical fires, electrical shocks, and other electrical hazards. Electrical safety training is essential for anyone who works with or around electricity. Electrical safety training programs provide information on the hazards of electricity, safe work practices, and the proper use of electrical equipment. These programs are designed to help people avoid electrical accidents and injuries. The Occupational Safety and Health Administration, OSHA, requires that employers provide electrical safety training to employees who are exposed to electrical hazards. There are many different types of electrical safety training programs available, ranging from basic awareness training to advanced technical training. It's important to choose a training program that is appropriate for your job and your level of experience. Electrical maintenance is essential for keeping your electrical system in good working order and preventing electrical problems. Electrical maintenance includes tasks such as inspecting electrical equipment, tightening connections, cleaning equipment, and replacing worn or damaged parts. Regular electrical maintenance can help prevent electrical fires, electrical shocks, and other electrical hazards. It's important to develop a comprehensive electrical maintenance program that is tailored to your specific needs. This program should include regular inspections, testing, and preventive maintenance tasks. Electrical troubleshooting is the process of identifying and resolving electrical problems. Electrical troubleshooting requires a systematic approach and a thorough understanding of electrical principles. When troubleshooting an electrical problem, it's important to start by gathering information about the problem. This includes asking questions about what happened, when it happened, and what symptoms are present. Once you have gathered enough information, you can begin to test the system to identify the cause of the problem. There are many different tools that can be used for electrical troubleshooting, such as multimeters, clamp-on ammeters, and circuit tracers. It's important to use the right tool for the job and to follow proper safety procedures. Electrical repairs should only be performed by qualified electricians. Electrical repairs can be dangerous and should only be attempted by someone who has the proper training and experience. When performing electrical repairs, it's important to follow all safety precautions and to use the proper tools and equipment. It's also important to ensure that all repairs are code compliant. If you are not comfortable performing electrical repairs yourself, it's best to hire a qualified electrician. Electrical upgrades may be necessary to improve the safety, reliability, or capacity of your electrical system. Electrical upgrades can include tasks such as replacing old wiring, adding new circuits, and installing new electrical equipment. When planning an electrical upgrade, it's important to consider your current and future electrical needs. You should also consult with a qualified electrician to ensure that the upgrade is code compliant and that it meets your specific requirements. Electrical safety audits can help identify potential hazards and ensure that your electrical system is safe and code compliant. Electrical safety audits are typically performed by qualified electrical safety professionals. During an electrical safety audit, the auditor will examine the electrical system for any signs of damage, wear, or improper installation. They will also test the system to ensure that it is functioning properly. If any problems are identified, the auditor will provide a report outlining the necessary repairs or upgrades. Electrical safety audits can help prevent electrical fires, electrical shocks, and other electrical hazards. The National Electrical Code (NEC) is a comprehensive set of standards for the safe installation of electrical wiring and equipment. The NEC is updated every 3 years, and it's important to stay up to date on the latest requirements. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is not a law, but it is widely adopted by state and local jurisdictions. It's important to comply with the NEC to ensure that your electrical system is safe and code compliant. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to return to the source, while bonding connects non-current carrying metal parts together to create a low impedance path for fault current. Proper grounding and bonding can help prevent electrical shock and fire. The NEC provides detailed requirements for grounding and bonding in Article 250. Overcurrent protection is designed to protect electrical circuits from overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, interrupt the circuit when the current exceeds a safe level. Proper overcurrent protection is essential for preventing electrical fires and damage to equipment. The NEC provides detailed requirements for overcurrent protection in Article 240. Wiring methods refer to the different ways that electrical wiring can be installed. The NEC recognizes a variety of wiring methods, including non-metallic cable, metal-clad cable, conduit, and wireway. The choice of wiring method depends on the application and the environmental conditions. The NEC provides detailed requirements for wiring methods in Chapters 3 and 4. Electrical equipment must be properly installed to ensure its safe and reliable operation. The NEC provides detailed requirements for the installation of electrical equipment in Chapter 4. These requirements cover topics such as equipment location, mounting, and wiring connections. It's important to follow the NEC requirements to ensure that electrical equipment is installed properly. Electrical safety is a shared responsibility. Everyone who works with or around electricity has a responsibility to follow safe work practices and to report any potential hazards. By working together, we can create a safer electrical environment for everyone. The voltage drop in a circuit is the decrease in voltage from the source to the load. Voltage drop can be caused by the resistance of the conductors and the current flowing through them. Excessive voltage drop can cause equipment to malfunction and can even damage equipment. The NEC recommends that the voltage drop in a branch circuit should not exceed 3% and that the voltage drop in a feeder circuit should not exceed 5%. Conductors must be sized properly to minimize voltage drop. The ampacity of a conductor is the maximum amount of current that it can carry safely without overheating. The NEC provides tables that list the ampacity of different types of conductors based on their size, insulation, and ambient temperature. Conductors must be sized properly to ensure that they can carry the expected load current without exceeding their ampacity. Short circuit current is the high current that flows when there is a short circuit in an electrical circuit. Short circuit current can be very dangerous and can cause severe damage to equipment. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the circuit quickly when a short circuit occurs. It's important to select overcurrent protection devices that are properly rated for the available short circuit current. Ground fault current is the current that flows when there is a ground fault in an electrical circuit. A ground fault occurs when a live conductor comes into contact with a grounded metal part. Ground fault current can be very dangerous and can cause electrical shock. Ground fault circuit interrupters, GFCIs, are designed to detect ground faults and interrupt the circuit quickly. It's important to install GFCIs in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor areas. Arc flash is a dangerous electrical explosion that can occur when there is a fault in an electrical circuit. Arc flash can cause severe burns, blindness, and even death. Arc flash hazards are present in many electrical workplaces. It's important to conduct an arc flash hazard assessment to determine the potential arc flash hazards and to implement appropriate safety measures. Safety measures can include wearing personal protective equipment, using insulated tools, and energizing equipment before working on it. The NEC provides detailed requirements for arc flash hazard assessments and safety measures in Article 110.16 and 130. The term ground in electrical systems refers to a connection to the earth, which serves as a reference point for voltage and provides a path for fault current to return to the source. Grounding is essential for electrical safety, as it helps to prevent electrical shock and fire. The NEC provides detailed requirements for grounding in Article 250. The term bonding in electrical systems refers to the connection of non-current carrying metal parts to create a low impedance path for fault current. Bonding is essential for preventing voltage differences between metal parts, which can create a shock hazard. The NEC requires bonding of all metal enclosures, raceways, and other metal parts that are likely to become energized. The term neutral in electrical systems refers to the conductor that carries the unbalanced current in a 3-wire or 4-wire system. The neutral conductor is typically grounded at the service equipment. The neutral conductor must be sized properly to carry the expected unbalanced current. The term hot in electrical systems refers to the energized conductors that carry the current from the source to the load. Hot conductors are typically black or red in color. Hot conductors must be properly insulated to prevent electrical shock. The term circuit breaker refers to an overcurrent protection device that automatically interrupts the circuit when the current exceeds a safe level. Circuit breakers are resettable and can be used repeatedly. Circuit breakers are typically used in residential, commercial, and industrial electrical systems. The term fuse refers to an overcurrent protection device that interrupts the circuit when the current exceeds a safe level. Fuses are not resettable and must be replaced after they have been blown. Fuses are typically used in a variety of electrical systems. The term transformer refers to an electrical device that changes the voltage of an alternating current. Transformers are used to step up or step down voltage to match the requirements of different electrical equipment. Transformers are typically used in power distribution systems. The term generator refers to an electrical device that converts mechanical energy into electrical energy. Generators are used to provide backup power during power outages. Generators are typically powered by gasoline, diesel, or natural gas. The term motor refers to an electrical device that converts electrical energy into mechanical energy. Motors are used to power a wide variety of equipment such as pumps, fans, and compressors. Motors are typically powered by alternating current or direct current. The term lighting refers to the use of electricity to provide illumination. Lighting is used in a wide variety of applications such as homes, offices, and factories. Lighting can be provided by incandescent lamps, fluorescent lamps, light-emitting diodes, LEDs, and other types of lighting fixtures. The term receptacle refers to an electrical outlet that provides a point of connection for electrical equipment. Receptacles are typically used to provide power to lamps, appliances, and other portable electrical equipment. Receptacles are typically rated for 15 amps or 20 amps. The term switch refers to a device that is used to control the flow of electricity in a circuit. Switches are used to turn lights and other electrical equipment on and off. Switches are typically rated for 15 amps or 20 amps. The term conduit refers to a pipe or tube that is used to protect electrical wiring. Conduit can be made of metal or plastic. Conduit is typically used in commercial and industrial electrical systems. The term wireway refers to a metal trough or channel that is used to support and protect electrical wiring. Wireway is typically used in commercial and industrial electrical systems. The term cable tray refers to a metal structure that is used to support and protect electrical cables. Cable tray is typically used in commercial and industrial electrical systems. The term insulation refers to the material that is used to insulate electrical conductors. Insulation is used to prevent electrical shock and short circuits. Insulation is typically made of plastic, rubber, or other non-conductive materials. The term grounding electrode conductor refers to the conductor that connects the grounding electrode to the equipment grounding bus. The grounding electrode conductor must be sized properly to carry the expected fault current. The term equipment grounding conductor refers to the conductor that connects the non-current carrying metal parts of electrical equipment to the grounding system. The equipment grounding conductor provides a low impedance path for fault current to return to the source. The term bonding jumper refers to a conductor that is used to connect two or more metal parts together to create a low impedance path for fault current. Bonding jumpers are typically used to bond metal enclosures, raceways, and other metal parts that are likely to become energized. The term ground fault circuit interrupter (GFCI) refers to a device that is designed to protect people from electrical shock by detecting ground faults and interrupting the circuit. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas where there is a high risk of electric shock. The term arc fault circuit interrupter (AFSI) refers to a device that is designed to protect against fires caused by arcing faults. AFSIs are required in many locations such as bedrooms, living rooms, and dining rooms to protect against the risk of fire. The term surge protective device (SPD) refers to a device that is designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other electrical disturbances. SPD are typically installed at the service entrance and at sensitive electrical equipment. The term uninterruptible power supply (UPS) refers to a device that provides backup power to electrical equipment in the event of a power outage. UPS are typically used to protect computers, servers, and other critical electrical equipment. The term power quality refers to the quality of the electrical power that is delivered to electrical equipment. Poor power quality can cause equipment to malfunction and can even damage equipment. Power quality problems can include voltage sags, voltage swells, harmonics, and transients. The term energy efficiency refers to the use of less energy to perform the same task. Energy efficiency can be achieved by using energy-efficient equipment, improving building insulation, and reducing energy waste. The term renewable energy refers to energy that is derived from natural sources such as sunlight, wind, and water. Renewable energy sources are sustainable and do not produce greenhouse gases. The term smart grid refers to an electrical grid that uses technology to improve its efficiency, reliability, and security. Smart grids can monitor and control the flow of electricity in real time. The term electrical safety program refers to a comprehensive set of policies, procedures, and practices that are designed to protect workers from electrical hazards. Electrical safety programs should include training, hazard assessments, and safety audits. The term qualified electrical worker refers to a person who has the training and experience to safely work on electrical equipment. Qualified electrical workers should be familiar with the NEC and other applicable electrical codes and standards. The term electrical safety culture refers to a workplace environment where electrical safety is a priority and where workers are encouraged to report potential hazards. A strong electrical safety culture can help prevent electrical accidents and injuries.